So welcome back to my talk. So here what I'm going to do is I'm going to explain you how to prove our theorems 1 to 4. So what we have to do, as we have seen before, we have to construct spaces in which we can isometrically embed our manifolds. So I'm going to embed M0 and Mj into a bigger space. Here, don't pay too much attention to the variables lambda and kappa. But what is going to happen is that since I isometrically embed M0 and Mj, we will be able to calculate the flat distance between the push forwards in this bigger space. And then what we are going to do is we are going to take the lim sup when j goes to infinity, and we are going to take this limit when kappa goes to infinity and lambda goes to 0, and we will get that this converges to 0. And because we know that the flat distance of the push forwards is an upper estimate of the intrinsic flat distance between M0 and Mj, we will be able to conclude. So I'm going to give more details about this, but this is the general picture. So let me start with, again, with proof of theorems 1 and 2. So for theorems 1 and 2, remember that we don't have boundary, or if we have boundary, we are requiring that M0 has totally convex interior. So the steps that we have to follow are the following. First step, we have to recall the previous theorem by Brian Allen and Cristina Sormani, in which they proved that the distance functions converge to the 0. This is up to a subsequence, and this is almost everywhere. So once that we recall this theorem, we will use it to find sets W lambda kappa contained in M, which one, the distance dj is going to be very close to the distance d0. We know that actually this distance dj is bigger than d0, but we want now that in the sets W lambda kappa, dj is bigger than d0, but not too much. And this not too much is reflected by this 2 lambda plus 2 delta lambda kappa j. And also we will like that this set W lambda kappa has big volume. So that means that the complement has very small volume. So, and this is written in this way. Since the volume of Mj will converge to the volume of M0, this quantity is going to be small. And this kappa, we will be able to take it big. So kappa is at the end is going to go to infinity. So volume of M0 divided by kappa is going to be very small. So we have that the volume of the complement of W lambda kappa is small. And then once that we have these sets, W lambda kappa, we will be able to construct a bigger space, zeta lambda kj, in which we can isometrically embed M0 and Mj. And then, as I explained before, we will take the lim sup and the lim of the flat distances, and this will converge to 0. Okay, so let's move on. And now, in order to prove theorem 3 and theorem 4, we have very similar steps. So step 2 is going to be the same, step 3 is going to be the same, but here we won't be able to use Brian Allen and Cristina Sormani's result. So we will have to prove convergence of the distance functions to the 0 almost everywhere. So let's continue. So here I'm going to explain to you how to construct these big spaces in which we would like to isometrically embed and calculate the flat distance. So for that, I'm assuming number 2. So number 2 was the existence of a set W. And this set, remember that it should have, the complement should have very small volume. And the distance dgj should be very, very similar to the distance dg0. And we are allowing an error of 2 delta j, some small error. So under these conditions, we will be able to construct a space. So this is a space set And this space looks like this. So first, in this middle part, I have a cylinder like the one that I talked about in my previous parts of this talk. So it's mj times an interval. And then what we are going to do is we are going to glue a copy of m0, and this is just using the identity function. And we are going to glue a copy of mj. And here what we do is we just identify the points in the closure of W. So here I have, I'm identifying these points. And we have to define an appropriate metric. So the appropriate metric is as follows. If you have 2 points in this space set, you can join them by a curve. And this curve, you can break it into pieces, the piece that is in M0, the piece that is in MJ times the interval, and the piece that is in MJ. So once that you break your curve into these 2 pieces, you can take the length of this curve. And then you want to minimize the length of all these curves that join these 2 points in set. With this metric space, it's very easy to isometrically embed M0 because M0 has smaller distances than MJ. And then what is crucial to isometrically embed MJ is this estimate. So this height, HJ. You really need certain height in order to isometrically embed. Otherwise, if you have 2 points in the top, so that means in MJ times HJ, you could have 2 points in the top, which in this space set could have a smaller distance if you go to the bottom to M0 and then you go back to the top. Okay, but we are able to isometrically embed, so that's not a problem. And once that we have this isometric embedding, we can calculate the flat distance of the push forwards. And what we get is the following estimate. So this estimate is going to be 2 times Vj, and remember that Vj is the volume of the complement of W, and plus these other two terms. And these other 2 terms, look, they are related to Mj times 0Hj. So this is Hj, volume of M, and then Hj plus the volume of the boundary Mj. So this looks very similar to the examples that we had before. Okay, so let me continue with this term, explaining this term. So what we have, our space set looks more or less like this one. So here I have M0, and M0 has smaller distances, and that's why it's thinner. And then we have MJ, and MJ has bigger distances. So when we glue a copy of M0, what happens to a cylinder M times an interval is that it shrinks. So the bottom is shrinking. So this space is no longer a manifold, but a metric space. And then in the top part, we are gluing a copy of MJ. And we are gluing identifying points in a set W. So this red part represents W. And the complement of W is this blue part. So we have this blue part in the copy that we are gluing, and this blue part in MJ times 0HJ. Same for here. And if we want to calculate the flat distance, well, because we have a distance increasing function between this cylinder and this part, except this M minus Wj, we will be able to calculate the flat distance. And then one more observation is that the picture is actually like this. In this picture, MJ is the blue part and the yellow part, and M0 is the inside. So I'm choosing W to be just the blue part. So W is the part that has distances very similar to M0. It's very close. So here the yellow part, the distances are becoming bigger. And also W has a big volume. So see, this blue part has big volume and the yellow part has small volume. Okay, so now let's continue. So once that we know in which spaces we can isometrically embed and calculate our flat distance, and notice that these spaces are actually very good because this volume, this Vj is actually small, and this Hj is actually also going to be small, and this volume Mj is going to be bounded, and this volume of boundary Mj is also going to be bounded. So these are very good spaces. So now we need to know how to get a set W that satisfies the conditions that we need. So this is a lemma that was proven by Allen, myself, and Sormani, and that we rewrote, Allen and myself, for a manifolds with boundary. And it says the following. So if you have almost everywhere convergence of the distance functions, so the dj converges to the 0 point wisely almost everywhere, then there exists a set W lambda kappa containing M that satisfies the conditions that we want. So the distance dj is very close to the 0, and it's actually dj is less or equal than the 0 plus some small term just in the set W lambda kappa, and the volume of W lambda kappa is almost the volume of Mj. Okay, so this already I explained, but let me tell you how to construct this set W lambda kappa. So this set W lambda kappa is constructed as follows. So lambda and kappa are going to be parameters, but using these parameters, we can choose an epsilon such that all the balls in my manifold M0 of radius lambda have this volume estimate. So all these balls have volume greater or equal than 2 kappa epsilon volume of M0. And this can be done using Bishop-Gromov volume comparison because we have a fixed manifold M0. So then this manifold, since it's compact, it has a Ricci lower bound, and we can apply Bishop-Gromov volume comparison. Okay, so once that we have this, we will use this volume estimate at the end of the construction of W lambda kappa. But let's continue. So because we have as a hypothesis that the distances dj converges to the 0 almost everywhere, we can use Egorov's theorem, and Egorov's theorem tells us that there exists a set given an epsilon. There is a set S epsilon which has big volume. So volume of S epsilon is almost the volume of M0 times M0. So 1 minus epsilon whole square M0, where the distances dj minus d0 converge to 0. And so we quantify this convergence with delta lambda kappa j, and for all the points in this set S epsilon. So once as we have this, we do the following. So I have S epsilon, and now I look at all the points that are given in the following way. So I fix a P, and then I look at the points PQ that are contained in this S epsilon. And because S epsilon has big volume, we know that almost everywhere, these slices are also going to have big volume, and they actually have volume bigger than 1 minus epsilon times the volume of M0. And because of this happens, what I'm going to do is I'm going to define our set, the one that we're looking for, W lambda kappa, as the set of all the P's such that these slices have big volume. And I'm quantifying this big volume as 1 minus kappa epsilon volume of M0. So this number is a little bit, well, it's smaller than this 1 minus epsilon volume of M0. So I'm collecting points that have big volume, but not as big as this one. I'm allowing certain I'm relaxing this condition. So then this is the set that I propose as the one that works. So now I have to verify the volume estimates, that it has very big volume, and the distance estimates. So for that, because of the way I define W lambda kappa, and because the way I define S epsilon, or the way I found it, we actually have that the volume of W lambda kappa is greater or equal than this. And once that we have this, what we can do is, because we have Gj greater or equal than G0, we can conclude this condition. So one of the conditions that we required, that W lambda kappa, the complement of it, has a very small volume, and it's given in this way. So we have the volume of Mj minus the volume of M0, the absolute value, and here we will have volume M0 divided by kappa. Okay, so now I just need to tell you how the distances behave, dj and d0. And for that, so take sp1 epsilon and sp2 epsilon. And here, these slices come from points p1 and p2 in W lambda kappa. So then they have big volume. And because they have big volume, by their definition, actually, the volume of this intersection is going to be greater or equal than 1 minus 2 kappa epsilon and the volume of M0. Okay, so that's very easy to prove. And the next thing is that what we can say is that the intersection of sp1 epsilon intersection of sp2 epsilon, there should be an x, so some x in our manifold M, such that the ball around this x of reduced lambda should intersect this sp1 epsilon and sp2 epsilon. So the reasoning behind this is that if there is no such x, then there will be a ball of this form of radius lambda that does not intersect sp1 epsilon intersection sp2 epsilon. So because they don't intersect each other, then I can calculate the volume of the union. So the volume of the union of the ball with this other set is going to be equal to the volume of the ball plus the volume of this other set. And this is going to be greater or equal than 2 kappa epsilon volume of M0 plus 1 minus 2 kappa epsilon volume of M0. And that is bigger than volume of M0. So this is a contradiction. So then that point X has to exist. So once that I have these points, I can actually calculate the distance between 2 points P1 and P2 in W lambda kappa. So what we have to do is use the triangle inequality. So because we have that this is non-empty, there is going to be a point that is in the ball that is also in sp1 epsilon and that is also in sp2 epsilon. So I can go from P1 to this point in the intersection and calculate the distance. So I'm going to get a lambda. Then from this point in the intersection to P2, and then I'm going to get this delta lambda kappa j. And then from this point in the intersection to P2, and I'm going to get another lambda. So I have the estimate that I mentioned. Okay, so then this proves what we wanted. So in order to conclude, we have the convergence of the distance functions, almost everywhere convergence of distance functions. This implies that we can select a subset W lambda kappa of M that has the nice conditions. And then with this W lambda kappa, we can construct a set lambda kappa j in which we can isometrically embed, so we can calculate this flat distance of the embeddings. And we know that this is bounded by 2 times the volume of the complement of W lambda kappa plus these volumes. Okay, So now what we do is we take j and kappa to infinity, and when we take j and kappa to infinity, we get 2 times lambda d plus lambda squared 1/2, but then we can take lambda to 0, and so we get 0. So then this part is going to become 0, this part is going to become 0, and the volume of the complement of W lambda kappa also converges to 0. So we are done with the proofs of theorems 1 and 2. Now, in the last part, I want to explain how to prove almost everywhere convergence of the distance functions when we do have boundary, because this was not proven by Allen and Sormani. So Allen and myself proved the following theorem. So here's where we have the strict inequality of the Riemannian tensors. We have the diameter bound, the volume convergence, and we require the convergence of Gj minus G0 restricted to the boundary, well, the Lm minus 1/2 norm to converge to 0. And then we conclude that up to a subsequence, djk converges to the 0 pointwisely almost everywhere. Okay, so let me give you an idea of how this theorem is proven. So what we are going to have is the following. So we start with our manifolds Mj. And what we are going to do is we are going to construct a doubling of our manifolds. So this Mj delta means that we are doubling our manifold. And let's look at this picture. So in this picture, I have 2 manifolds that are the same. One is in the bottom and the other one is in the top, and they are joined by a cylinder. So here in this figure, Mj delta is this cylinder boundary of Mj times this interval 0 delta. So it's this part. And then we are gluing a copy of Mj in the bottom and a copy of Mj in the top. And we need to define a Riemannian metric. So this Riemannian metric is actually defined in such a way that in Mj, in both copies of Mj, is the same as Gj. And it has to satisfy another nice conditions in order to conclude that we have the convergence of the distance functions. But okay, so let's say we have these doublings, and now I take 2 points P and Q in M, and I can see them in a copy of M delta I. And once that I see them in a copy of M delta I can use triangle inequality to calculate the distance, the dj distance between P and Q minus the d0 distance between P and Q. So here I will have a triangle inequality. And then in this triangle inequality, what we have is these distances in brown. So in these distances in brown, I have a fixed manifold. So here I have manifold Mj, and here I have manifold M0. And what we are buying is the doublings. And then in this part in the middle, what I'm doing is I'm changing J. So I'm buying manifold, but the cylinders that I have here, they have the same distance delta I, the same height delta I. So let me continue. Okay, so what we prove is that when we have a fixed manifold Mj, but we are buying the height of our doublings, we have this uniform condition. So this uniform condition is going to depend on delta I, and this is the diameter, and this eta is just a constant. So we have that this first part and third part in this triangle inequality satisfies this condition. So it's very nice because in the limit we can take I to to infinity, and notice that in the limit delta I goes to 0. So we will get that the first part and that the third part converge to 0. And then for the middle part, what we want to use is the theorem of Allen and Sormani. And we are able to use it because, well, notice that the doublings are manifolds that don't have boundary. And because of the conditions that we impose, we are able to show that the volumes of these doublings converge to the volumes of this manifold, that they have diameter bound, and that the G0 delta I is less or equal than the Gj delta I. So we can use Allen-Sormani, and then well, we look at this triangle inequality again. We take the lim sup with respect to k, and we take the lim with respect to I, and we get in the limit a 0. So that's all. And now I want to conclude with open problems and questions about our theorems. So the first question is it possible to relax the conditions on the boundary? So remember that in one of the theorems, we required that Gj minus G0 restricted to the boundary, that their Lm minus 1/2 norm converges to 0. And in the other one, we required that Gj minus G0 converges to 0 with respect to the Lm/2 norm, plus this uniform volume bound on the boundaries. Question number 2. What about if the Mj are diffeomorphic, but we expect the limit not to be diffeomorphic to any Mj, and this situation can happen, for example, when Mj is an annulus, so each of them is an annulus, but this annulus converge to a ball. The third question is, what about if Mj are not diffeomorphic? And number 4 is, can these theorems, so theorems 1 to 4, be used to prove a more general positive mass theorem and tori stability results? And number 5, I mean more general, can we use theorems 1 to 4 to prove results that involve scalar curvature bounds? Okay, so before I finish, let me mention, I didn't say it before, that there is a compactness theorem for integral Coriolis spaces, but you don't know what's the limit. So it's very good to know what's the limit in order to solve some important geometric problems. And finally, here is a list of papers that I cited in this part of my talk. Thank you for your attention. If you have any questions about my talk or about intrinsic flat convergence, please email me at raquel.peralezaguilar@gmail.com. And thank you very much.